data data science creators, data science users, and the data science, how secure, how effectively you're going to transfer the data without any problem. So in this connection, I would like to request all the participants and delegates from other institutions also, please try to involve yourself actively and learn new technologies which are available in data science. And that way, I think we can upgrade ourselves in the latest developments, especially in case of the data science, because handling of data is very, very important. How securely I think you're going to handle the data and how effectively you're going to retrieve the data. These are the two things which are very, very important. So in this connection, I think all experts, I think they're going to deliver the lectures during this 1 week, and you'll have a great learning. I hope you're going to enjoy this 1 week. Finally, at the end of the day, definitely you're going to learn some important techniques which are very, very useful. And in turn, I think you're going to transform that knowledge into the students. So that is the main objective of organizing this PDP programs. I wish you all good luck. I hope, I think you're going to enjoy this week. Thank you.
Thank you. Thank you so much, sir, for your kind wishes. Thank you, sir. I request all participants to turn off your videos so that I will share my screen. Entire screen.
Who's going to?
Yes. Good morning, all of you. Am I audible?
Yes, sir.
Yes, sir.
Yes, today we will try to understand one of the important concept in machine learning. Just give me 1 or 2 minutes time.
Okay.
Yes. Actually, in Google, just I typed this one, dimensionality reduction in machine learning. Is it visible? Just see how what it gives. It is giving so many blocks, dimensionality reduction for machine learning. There are so many articles. What is dimensionality reduction? Overview, popular methods, 11 dimensionality reduction techniques. There are so many things. Even if you go for image search, just I am searching images on this particular topic. Just see what it gives. It gives so many articles. If you see, you can observe so many people discussed about so many data sets. In this particular lecture, I'm in this particular PDP, Professional Development Program, I'm referring this particular blog. This is one of the famous blog written by Christopher Wola. Just I would like to show you this blog one so that I will continue my discussion. Actually, what it says, it is published in 2014, is one of the greatest machine learning engineer. What it says, visualizing MNIST and exploration of dimensionality reduction. Just let me go through these pages. Actually, he collected a data set. This is basically MNIST data set. Just see this one. MNIST is a simple computer vision data set. In this particular session, I will explain about this particular data set and we will try to understand how we can write. This is a case study on dimensionality reduction. If you speak strictly, it is useful the people who are writing research papers, applying projects, and even it is helpful for students. We will try to understand end to end this case study. What it says basically, I request participants to mute yourself. This is basically computer vision data set. In this particular data set, I have images. What is this image size? Each image size is 28 by 28 pixels. What are these images? Basically, these are handwritten digits. Just let me go through this blog so that I will explain what is it. Next, what it says, this image, this is a handwritten digit 1. How they are representing what is this Kola saying? This machine learning engineer saying that every handwritten image is represented by using 28 by 28 matrix. Means we are representing each image by using a matrix. If we speak strictly, even now everyone is saying deep learning, convolutional neural network, where we need images. First, we must understand what is image. In computer, how we can represent image? We can represent image in the form of a matrix. How system can understand this image? For example, this is handwritten digit 1. How they are representing? Just count this. How many rows are there? There are 28 rows and there are 28 columns. How is he representing? Just see, this white portion is representing this white portion by zeros, and this black portion is representing by 0.7, 0.6, 0.4, 0.1, 0.3 like this. Why? Because the 0.7 means it's dark one. 0.4 means little bit less dark. 0 means completely white. In computer, we can represent an image by using this matrix. Now I know how to represent an image. For example, this is a data set. If I go to Wikipedia once, what is this? This is Wikipedia article which says MNIST database. Just see this, how many they are writing digits. What is this MNIST? MNIST means Modified National Institute of Standards and Technology database. It is one of the important database. It is one of the important data set in image processing, machine learning, data science, artificial intelligence. Basically what it says, just see, all these digits are handwritten digits. People may write 0 in different manner. Just see, people may write 1 in different manner. People may write 2 in different manner. Different people may write these digits in different manner. How many such images are there? The MNIST database contains 16,000 training images, 10,000 testing images. We will discuss in next session, maybe tomorrow or day after tomorrow, what is the training, what is the testing, what is the cross validation. Time being, just understand that this is a data set in which you have 60,000 training images, 10,000 testing images. 60,000 training images means maybe 5,000 images related to digit 1, maybe 10,000 images may be related to digit 2. There are few thousands of images related to digit 0, few thousand related to digit 1. Totally, you have 60,000 images, isn't it? Yes, this is about MNIST data set from Wikipedia article. Actually, we are discussing about this block. Now let us try to understand. There are 60,000 training images. Now we will try to understand about training images. What is testing? What is cross validation? All those things I will discuss in next session. That is in tomorrow's session. Time being, just understand. We know how to represent single image. This is single image. How many such images are there? From 0 to 9, 10 digits. If they collected 60,000 images. Now what they did, just see, since each image is 28 by 28 pixel, what they are doing, we can flatten each array into 28 into 28. If you multiply 28 into 28, you will get 784 dimensional vector. Means he is converting each image into a vector. Actually here what's happening? For example, just let me write here so that it may be little bit you may get little bit clarity. Just see here what's happening here. Here I have an image. What is that image? Just see. Let me change color. Otherwise, let me say there is a digit 1, handwritten digit 1. It is represented by using 28 by 28 pixels. Now this is about single image. This is one image. How many such images are there? There are 60,000 images. First, we will try to understand about single image. This is single image. If you speak strictly, how this image look like? It looks like there are 28 rows, 28 columns, isn't it? This is 28 by 28 matrix. He is flattening this one. Flattening means what? Flattening. That's what that block says. What is flattening? For example, simple example, let me say 2 by 2 matrix. 1, 2, 3, 4. How can I flatten this one? Just there is two techniques: row flattening and column flattening. Let me say, let me assume I'm applying row flattening. Row flattening means what will I do? I will take first row. I will keep. Please try to mute yourself. There is second row I am keeping like this. Means actually this is 2 by 2 matrix. I'm converting this 2 by 2 matrix into 4 by 1 column vector. This is by default, if I say vector, what does it mean? It is column vector. This 2 by 2 matrix is converted into 4 by 1 column vector. In similar manner, just see 2 into 2, 4, we are converting into 4 by 1 matrix. 4 by 1 matrix in the sense it's a column vector, isn't it? By default, it's a vector. In similar manner, if I multiply 28 into 28, I will get 784. This particular 28 by 28 matrix, I can convert into 784 by 1. This is about single image. Let me say this is X1. X1 means my image 1. How many? Let me say my data set is D equal to Xi comma Yi, I equal to 1 to 60K. What does it mean? In my data set, I have 60,000 images. X1, X2, so on X60,000. What is my Yi here? My Yi means labels. How many labels are there? 0, 1, 2, 3, so on 9 labels. That your digit may belongs to any one of these labels, 0 to 9. Yes. Now, anyway, let me repeat this one. This 2 by 2 matrix I am representing as 4 by 1 column vector. In similar manner, this 28 by 28 matrix I can represent as 784 by 1. This is representation of one particular image. Let me say that is X1. How many such images are there? There are 60,000 images. First, I must construct a data set. How can I? This is X1. What is my X1? X1 is, just see, what is my X1 here? My X1 is, what is the size of that vector? My X1 is 784 by 1. In similar manner, what is my X2? Second image. This is also 784 by 1. So on. How many such images are there? There are 60,000 images. What is the size of my 60,000 image? Again, it is 784 by 1 column vector or vectors. Now, I must represent capital X. Capital X means what? Capital X means data set. What is my data set here? My data set is MNIST data set. How can I represent this matrix? Xi whole transpose. How it is Xi whole transpose? My first row is X1 transpose. In this capital X matrix, I kindly request all the participants to mute yourself. If you have any discussion, anyway, we will at the end of the session we will discuss. I will be available throughout this week. Throughout this week, you can discuss. We can discuss and we can share whatever we learn. Yes. What is my first row? My first row is X1 transpose. That is related to some image. X1 transpose means, what is my X1? X1 is 784 by 1. Transpose means what? This column vector will become row vector. This is 1 by 784. What is my X2 transpose? That is second image. Second image is transpose means, again it is 1 by 784. In similar manner, how many images can I represent like this? I can represent 60,000 images. Last image is X60,000 transpose. Here also I will get 1 by 784. How many such images are there? Yes. Now, how can I represent my capital X, my data set, my training data set, my 60,000 images? My 60,000 images I can represent like this. How can I represent? Just see. This is 60,000 by 784. I think if you have any doubt, please express yourself. Why? Because this is first image, this is second image, this is third image, fourth image, 60,000 image. Each image I am representing in the form of a row. Each sample point in the context of data science, I can say each sample point I am representing. This is First one is X1 transpose, second one is X2 transpose, last one is X 60,000 transpose. Now I am able to represent entire data set in a single matrix whose size is 60,000 by 784. What will you find here? What is the 28 by 28 image we took? All those are pixel values, isn't it? Here, what will you get here? Pixel values. I have pixel value here. I have pixel value here. How many? This is pixel 0. If I speak strictly, this is pixel 0. This is pixel 1. In similar manner, what is my last pixel? My last pixel is pixel 783 because there are 784 columns. Actually, if you speak strictly, what is the dimensionality of this data set? Dimensionality means number of columns.
Okay.
What is, I request participants to mute yourself. What is the dimensionality of this particular data set? 784 dimensions. Why? Because you have 784 columns, isn't it? For example, if you recall, you might have learned about iris data set. What is iris data set dimensionality? You will have sepal length, sepal width, petal length, petal width. How many columns are there? There are 4 columns. In the case of iris data set, dimensionality of your data set is 4-dimensional data set. What is today's session? Here we are interested in understanding dimensionality reduction. Why we have to reduce dimensions? All those things I will discuss. Anyway, just give me few second times. Let me go back. Let me go back to this particular block. Just see what is he saying. Since each image has 28 by 28 pixels, we get 28 by 28 array. We can flatten each array into 784 dimensional vector. That's what I'm explaining. Each image is converted into a column vector whose size is 784 by 1, isn't it? That's how you have to represent data. After representing data, what we have to do, all these things I will explain. Just let me go back to my presentation. How it works, we will see. Just again, I will come back here while discussing about Tisne. Before starting this session, I would like to show you what I did. For future reference, maybe this session is very short. Why? Because within 2 hours, actually related to Tisne. Actually, there are 2 important dimensionality reduction techniques. One is Tisne and another one is principal component analysis. On this particular dimensionality reduction technique, our department worked rigorously. I think this work will be useful for students as well as participants. If someone is interested, what we did, we recorded 29 lectures only on this particular topic. Just if we start, for example, just what we did. What we did actually related to PCA, where we started, let me say lecture number, just give me 1 second time. Yes, MNIST dataset. In this particular lecture number 221 to, I can say lecture number 249. If someone is interested to understand in detailed manner, anyway, in this session, I will try to explain to maximum extent, but from lecture number 221 to just go through 249. I think as per my understanding, maybe almost 30 lectures. We recorded 30 lectures only on dimensionality reduction. Our department recorded all these lectures, only one intention. Why? Because dimensionality reduction is very, very important. We felt that there is a huge gap. So a huge gap to build some sort of video lectures here. That's why we built. Actually, just see, in this particular lecture 221, we explained what is MNIST dataset, how to load this dataset. Before understand, just go through this one, 221 to 249 lecture. Yes, first let us go. I will come back. Let us try to understand real motivation. What is the intention of this particular dimensionality reduction? Why do we need? Why we learn PCA? Why we need principal component analysis? Actually, if you speak strictly, there is one of the famous technique. There are 2 techniques in literature. The famous techniques are, one is PCA. PCA means principal component analysis. Another one is Tisne. This we will try to understand about these two techniques with help of simple data set. What is that data set? As I told you, MNIST data set. I will explain one simple Python code. This is one of the best case study in machine learning or data science. First, why do we learn? Why? What is the intention? Why you have to learn whether it is PCA, whether it is TSNE? What is why do we need these techniques? If you observe carefully, humans have power of visualizing. Humans means we can visualize only 2D or 3D data. How can visualize this 2D and 3D data? Using scatter plots. In last week we conducted data visualization professional development program. There our experts discussed about all data visualization techniques. Means humans can visualize things in 2D and 3D by using a data visualization technique known as scatter plots. Whereas if you may have data with 4 dimensions, you may have data with 5 dimensions, you may have data with 6 dimensions. Even you can visualize 4-dimensional data, 5-dimensional data, 6-dimensional data by using pairwise plots in Python or in R programming. In last week, our Professor Manoj discussed. Anyway, you can visualize 4D, 5D, 6D data by using pairwise plots. In real scenarios or in real situations, we mostly have data set. More than 10 dimensions. Just if you observe any real-time data set, you can have at least 10 dimensions, isn't it? You may say, sir, Iris data set is having only 4 dimensions. Of course, it is. I can say it is toy data set. It's a toy data set, means this is data set which is meant for learning. But in reality, most of the data sets have more than 10 dimensions. But if it is having 10 dimensions, please, I request participants to mute yourself. Please mute yourself. If it is having more than 10 dimensions, our biggest problem is visualization. You cannot visualize. It is difficult to visualize. It is difficult to visualize 10-dimensional data set. Therefore, what we have to do? What is our MNIST data set? It is Xi belongs to RD. RD means what? How many dimensions it is having? 28 into 28 means 784 dimensions. Is it possible to visualize these 784 dimensions? It is not possible. What you have to do? Let me say, originally you have D dimensions. You have to convert into D dash dimensions. What is the relation between D dash and D? Your D dash must be less than D, isn't it? Yes. First we must understand why we have to reduce dimension, because to visualize. And another one is, there are machine learning algorithms, there are artificial intelligence algorithms, there are data science algorithms which may not work on high dimensional data. There are machine learning algorithms which may work only 100 dimensions. There are machine learning algorithms which may work only on 150 dimensions. In such case, we have to reduce dimensions. How to reduce dimensions? There is a beautiful mathematics behind it. We will try to understand that maths before understanding. I would like to show you one simple example. Anyway, let us try to understand one simple example, something like 2-dimensional to 1-dimension. You may ask me, why you are reducing 2-dimensional data? Anyway, you can visualize 2-dimensional data. What is the necessity of reducing 2D into 1D? It is only for understanding's sake. I am explaining this example only for understanding. What is linear algebra? The greatness of linear algebra is, if it is working for 2 dimension to 1 dimensions, you can extend this to higher dimensional. You can extend it to higher dimensional data. Yes. Now let us try to understand. How it works. Let me show another presentation. One picture I would like to show. Just just bear with me for few seconds, only few seconds. Yes, let me show. I have some data set like this. Yes, what is this particular data set? Just see geometrically what it says. Here I have a matrix. Let's take a simple data set. What is the dimensionality of this particular data set? Anybody can understand what is its dimension? Yes, 1 minute. Okay. Okay. Yes, this is my data set. How many points I have here? I have n points. First point, second point, third point, n points. For example, in MNIST training data set, I have 60,000 points. That's why we had 60,000 rows. How many columns we have here? I have 2 columns. Feature 1, feature 2. Therefore, number of columns 2. Therefore, dimension of this data set is 2. What is the order of this matrix? This order of this matrix is n cross 2. There are n rows and 2 columns. Let me say I have feature 1. Why? Let me assume my feature 1. Let me say like this. Suppose we have data set of students which comprises of 2 features. Features, what are the features? One feature is height and another feature is age. Feature 1, what is my feature 1? Age of the students. What is my feature 2? Feature 2 is height of the students. Yes. Now, what is the dimensionality of this particular data set? 2 dimensions. What is my intention? I must reduce this n by 2 matrix into n by 1 matrix. Means I would like to convert 2-dimensional data into 1-dimensional data. Once if it works, you can extend this to higher dimensional. Means you can extend 2D to ND. You can extend this 2D to ND means n-dimensional data, isn't it? As I told you, for simplicity only, I'm explaining this example. 2-dimensional to 1-dimensional. Now what happens? Just if I plot this one, just let me assume I plotted these features. Anyway, you know how to plot this one. You have data sets. You have feature 1, feature 2 data sets. You have feature 1 and feature 2. You know how to plot 2-dimensional data. This is a plot. If you observe carefully, actually variance. Actually, this is spread. Spread is very, very important. This is spread on feature 1, isn't it? This is spread on feature 2. In data science, in data science, in statistics, there is something like a concept known as variance, isn't it? There is another name for variance is spread. There is another name for spread. The spread is information. If you see the spread, if you see the spread on feature 1, compare this spread with this spread. Which spread? This spread. I have feature 1 on x-axis. I have feature 2 on y-axis. My intention is I have to reduce this 2D data to in 1D data. While reducing, what you have to do? You have to reduce such a way that you must lose minimum amount of data. Always remove the dimensions. So by which type of dimensions, which type of features will you remove, so that resultant data set must not lose much data, more data, isn't it? Here, which one is having more spread? I have feature 2 has more spread. Just see this spread. Just see the feature 2 length here, feature 1 length. Just if you measure with scale, this length is small compared to this length. Therefore, if I would like to convert this 2D data into 1D data, what I have to do? Which feature I can preserve? Certainly, 100% you will agree that you will retain. Which feature will you retain? I am retaining feature 2. I am removing feature 1. Why? Because its spread is very less. In a class, if you age, feature 1 is age, you may not find so much of variation in terms of age. That's why this spread has this has got less spread. Therefore, I am removing feature 1. I am retaining feature 2. This n by 2 matrix is converted into n by 1 matrix. Means your 2D data set is converted into 1D data set. Actually, here manually we are saying what happens. For example, our data set, my MNIST data set size is 60,000 into 784 dimensions. Now, I cannot visualize this particular data set. What is the reason? It has got 784 dimensions. My intention is I have to convert this capital X data set into 60,000 into 2. In the place of 784, I'm writing 2. Here in the place of n by 2, I'm writing n by 1. In this particular session, we will try to understand how to convert this 784 dimensions into 2 dimensions. Even after converting this 60,000 by 784 matrix into 60,000 by 2 size, how much of information you can retain, how much of information you will lose, that also we'll try to understand. Actually, that is the beauty of mathematics. In mathematics, there is something like eigenvalues and eigenvectors, or characteristic roots. Eigenvalues, there is another name people used to call as character roots, characteristic vector or eigenvectors. Eigenvalues and eigenvectors plays a big role, very big role in understanding, in converting this higher dimensional data into lower dimensional data. Actually, let me go back. Let me spend 1 or 2 minutes time here. Actually, I would like to show this one. Just bear with me for a few seconds before proceeding. Just see what we are saying about PCA. PCA means what? PCA means principal component analysis. Let me type principal component analysis. Let me say like this. Just let me search. Is invented. In which year it is invented, we will see. Just I request participants to check this one, in which year they invented, in which year this is invented or introduced. Just check it is invented by whom. Yes, just see. Principal component analysis first proposed by Carl Pearson in 1901. This is the beauty. In the year 1901, a great person introduced this technique. Still,
Requesting all the participants to please mute yourself.
HOD sir, please unmute yourself.
HOD sir, please unmute yourself.
Sir, you are muted. Please unmute your mic, sir.
Sorry. I think now is it visible? Yeah, am I audible?
Yes, sir. Now
Yes,
it is
sir.
audible, sir.
Yes, sir. Now
Yes.
it is audible.
Okay, maybe. Yes, actually what we are saying here we are saying about simple 3 by 3 matrix, isn't it? Now what is our matrix size? Is anybody can say what is the size of our training data set? What is the size of our capital X equal to? Yes, I think someone is muting. Please don't do it. Yes. Anyway, what we are saying, our matrix size is, what is our matrix size? My matrix size is 60,000 by 784. What we have to do? We have to find eigenvalues and eigenvector, but I cannot calculate. Why I cannot calculate? It is not square matrix. Now, this I will convert into square matrix. How can I convert into square matrix? All those things I will explain with the help of simple code, so that you can understand. Just let me show a few slides before explaining that code. Just see this one. This is one of the important slides. Actually, if you Google it also, you will get, just say geometrical interpretation of eigenvalues and eigenvectors. If you type something like that, you will get. Yes. Now, before explaining code, just I am taking 2 by 2 matrix. Why am I taking 2 by 2 matrix? It is easy to understand. Yes, let me consider I have 2 by 2 matrix here. 2 by 2 matrix means what? How many eigenvalues I will get? I will get for 3 by 3 matrix. Just try to recall your BTech days. For 3 by 3 matrix, you used to get lambda 1, lambda 2, lambda 3, eigenvector x1, x2, x3. As I have 2 by 2 matrix here, I will get 2 eigenvalues, lambda 1, lambda 2. In mathematics, generally we used to call x1, x2 as eigenvectors, but in this particular article, what they are writing, just type geometrical interpretation of PCA and just do image search, you will get this pic. This is a pic from particular blog. Just see this one. Let me say I have 2 eigenvalues, lambda 1 and lambda 2. Corresponding eigenvectors are v1 comma v2. My v1 is corresponding to lambda 1. My v2 is corresponding to lambda 2. Yes. Case 1. How many cases we have here? We have 4 cases. Let us try to understand one by one. In case 1, lambda 1 equal to 3, lambda 2 equal to 0. What is this lambda 1 equal to 3, lambda 2 equal to 0? Which one has got highest value? Lambda 1 has got highest value. Which one has got lowest value? Which one has got lowest value? Lambda 2. Corresponding to lambda 1, I will get an eigenvector v1. Corresponding to lambda 2, I will get an eigenvector v2. If you see the spread, if you see the information spread or information, or I can say variance. Spread or information or variance. I can find so much of data, or I can find so much of information. I can find almost all information. This is a vector, my dear friend. Just remember, v1 is eigenvector corresponding to lambda 1. v2 is an eigenvector corresponding to lambda 2. v1 is screen ratleda. Screen vastund kada. Huh? Is it not visible?
No, sir. It's
visible, sir.
Just I am writing. Please check it once. What am I writing? Is it a red color? Is it appearing?
Yes, sir.
Is it not?
Yes, sir. Yes, sir.
I am writing red. Is it there or not?
Yes, sir.
Yes. Someone is saying screen is not shared. Okay. Anyway, just my dear friend, this is a little bit important. Try to concentrate it once. Actually, what it says, I have eigenvector lambda 1, another eigenvector lambda 2. V1 is an eigenvector corresponding to lambda 1. V2 is an eigenvector corresponding to lambda 2. Understand here V1 comma V2 are vectors. I can find all information of that particular data set. Which data set? I already represented my data set by using 2 by 2 matrix. All information I can find along a vector known as V1 vector. I cannot find single information, single data points along V2. Why? Because your lambda 1 is bigger than lambda 2. Your V1, an eigenvector corresponding to highest eigenvalue will consist of more information. That's why just if you observe these data points, almost all data points spread along this particular V1 axis. You cannot see single point along V2 axis. Why? What is the reason? Reason is so simple. Reason is V1 is an eigenvector corresponding to highest eigenvalue. How much of information you can find along V1 means there is simple formula lambda 1 by lambda 1 plus lambda 2. What is my lambda 1? 3 by 3 plus 0. 3 by 3 plus 0 means 1. 1 means 100% data is along V1 axis only. How much of data is along V2 means that you have to calculate lambda 2 by lambda 1 plus lambda 2. That is 0 by 3 plus 0, 0. 0% of data along V2. Yes, this is case 1. For example, let me consider case 2. I have lambda 1, first eigenvalue 3, second eigenvalue is 2. How much of information I can find along V1? That is lambda 1 by lambda 1 plus lambda 2. That is 3 by 4. 3 by 4 into 100 means what is this? 425. 75% information I can find along V1. Only remaining 25% information I can find along a second eigenvector V2. In similar manner, what about here? How much of information I can find along V1? Just see. Lambda 1 by lambda 1 plus lambda 2. That is 3 by 3 plus 2. 3 by 5. 3 by 5 into 100. 5 2 means 60% of information I can find along V1. Only 40% of information I can find along V2. Isn't it? What about this? This is 50-50. Why? Because if 3 by 3 plus 3 in both the cases, 50% of information along V1, 50% of information along V2. Why we are discussing? In the case of dimensionality reduction, for example, here which feature will you remove? In this 2 by 2 matrix, which feature will you remove? You will remove feature 2. What is the reason? This feature 2 is related to smallest eigenvalue, isn't it? Here, which one will you remove? Again, always remove a feature, an eigenvector which is a feature. Otherwise, I can say feature which is corresponding to less eigenvalue. That is the basic motivation. That is the basic motivation behind this. Actually, it has got its own limitations. Let me Google search for it. Otherwise, just see this one. Let me go here. Yes. Let me search something like this one. Limitations of PCA. If I search something like this, what I am getting, just let me say image search. If I do image search, just see. This is one of the I can say this is one of the beautiful lecture explained by some person. Just I would like to show this one. Yes, this is limitations of PCA. How many cases are there? Anyway, otherwise I would like to show from even you. I explained it here. Maybe you can see where you can see. Yes, limitations of PCA means, just see this one, some column standardization. Just give me 1 or 2 minutes time. Just see limitations of PCA. What is this limitation? Just let me show that. Pick once. Let me mute this one. Maybe I think it's giving some sort of advertise. Just give me 1 or 2 seconds time. Yes. Just see this particular lecture, what it says. Actually, what it says. Yes, all those things maybe I'm explaining. Just see same pick. Just see same pick. These are the picks I collected. This is one limitation. Why it is limited? Limitation. Why? Because here circular. Maybe I discussed about 4 cases. What is my fourth case? Lambda 1 equal to 3, lambda 2 equal to 3. What does it mean? That is circular. Means you can find same sort of information along V1 and V2. If you don't know which one you have to drop. You don't know which sort of whether to drop V1 or V2. That is a difficulty here. Why? Because information spread equally along first eigenvector as well as second eigenvector. In such case, PCA doesn't work, isn't it? That's what I'm writing here. Of course, we were saying that there is another one. Just see, lambda 1 is approximately equal to lambda 2. In which case, what happens? We'll get same information along V1 as well as V2. That's the biggest difficulty. And there are cases here also. Actually, this is another case. Your problem is what happens in the case of PCA. We will project things. If I project things, what happens? If I project this data, your higher dimensional, actually you have less information along this particular axis. This one, you have huge information along this axis. If you project all these points on this axis, they will get overlapped. If possible, just listen this lecture. I explained so neatly, maybe because of just here. That's what I'm explaining. Just I'm projecting. If I would like to reduce this into single dimension, what I have to do? I have to remove V2. Why? Because it has got less spread. In such case, what will I do? I will project all the points along V2 on V1. In which case, these points and these points get overlapped. They will be projected on. They will get overlapped here. That is another drawback. And there are as we are saying, there is another limitation. What is that another limitation here? We have one nonlinear curve. If I project one dimension to another dimension, we may lose this beautiful shape. Yeah, this beautiful shape has got some sort of data set. You don't want to lose that particular data set. Anyway, just go through, and certainly you can understand. That's what this person is also explaining. Same thing. Maybe I explained with a little bit more sort of intuition. That you have to check. This is limit dimensionality reduction visualization. You can see there are so many blogs. There are so many. Just this one he is explaining in some other manner, but intention is same. You can find that particular picture also somewhere in some blog. There are many persons who are explaining this concept. Yes, if you search this particular pic also you will get. Anyway, that's what it says. Maybe it's 12 o'clock. As we have time constraints, let me proceed further. Now what we did, we know how to represent this data. Now I will explain. Actually, I will explain this demonstration. Actually, we will supply this IPython notebook. I will share all this PPT, as well as I will share this Python code also. Our coordinators will share this code. Actually, let me explain this code, how it works. There are a little bit mathematics is also there, as because we have some time constraints, as we have left with only 1 hour. That's why let me explain little bit code. There may be few gaps. Don't worry. I will be available throughout the week. Not only these, throughout the weeks. I will be available wherever you want, whenever you want. You can always interact with me. I'm happy to share. Always, I'm happy to share whatever I learned. Yes, let me explain this PCA with simple Python code. Actually, you can find this. You can find this particular. These are the limitations of PCA which we discussed. You can find this particular code. this particular data set in Kaggle. Just if you go to Kaggle, even you can see here this particular data set. Maybe just let me show, otherwise here, let me go back. If I go back, this one is, anyway, it may take time. I don't want to waste time. Just if you can find, just try to recall in beginning what we were saying. There is a training data set, isn't it? Just what I did, all of you might have worked many times with this particular data set, Kaggle data. Just go to Kaggle and write MNIST data set. Of course, I recorded all these lectures. Just if you go through also, you can understand. If you type MNIST dataset, you can find two files. One is train.csv, another one is test.csv. Just I downloaded train.csv file. What I did, I downloaded this train.csv file. Yes, I kept in E drive. There is a folder, applied data science with Python. In this particular folder, I kept this one. Now, what am I doing here? Just see. Of course, we know pandas. This is alias for pandas. Import pandas as PD. PD.read_CSV. This is a command or function or method, whatever it may be. This particular command is useful for reading a data set, a CSV data set. Underscore CSV means I'm reading CSV. I'm reading this particular CSV data set. What I'm doing before applying principal component analysis, let me try to understand the data set itself. Therefore, in Python, there is a simple command, print d0.head file. What is my d0? In d0, I have my entire data set. In d0, I have my entire. For example, what is my data set? My data set is 60,000 into 784 data set I have. Now, what am I doing? I am displaying only first 5 rows. I am not displaying this entire 60,000 rows. It's difficult to see in my screen. Therefore, head 5 means I am displaying first 5 rows, I can say. Why am I displaying first 5 rows? To understand the data set. Intention is to understand the data set, isn't it? Now, of course, there are labels. What is my label in this particular data set? Yi. My particular data set D equal to xi comma yi, I equal to 1 to 60,000. What is my yi? My yi belongs to a set 0, 1, 2, so on 9, isn't it? 0 to 9, any label, isn't it? Yes, here there is a column in that particular data set, label column. I'm keeping that in a variable L. Now I'm dropping that. D0.drop. I'm dropping access equal 1 means I'm dropping from columns. Which column? First label column I'm dropping. Now, what am I doing? For timing, I don't want, just it is some sort of data pre-processing. Now, what am I doing? Just see, this is print d0.head_file. This is output. Print d0. Actually, I would like to show IPython notebook directly, but difficulty is in IPython notebook, I cannot write this pen. That's why I'm keeping in slide and showing. Of course, I will share that IPython notebook. Yes. What's happening here? Print d0.head_file. By that time, I have not dropped this label. Still, label is available. Head_file means how many rows? 5 rows. What is first column? Label. What is my second column? This is pixel 0. I already discussed. This is pixel 0. This is pixel 1. This is pixel 2. This is pixel 16. Pixel 17. How many? What is the dimension of that particular matrix? 28 into 28. That is 784. Just see. You are getting from, if you observe carefully, you are getting from pixel 0 to pixel. This is pixel 783. This is pixel 0. This is pixel 0. Pixel 0 to pixel 783 means totally how many pixels? Pixel 0 to pixel 784. Isn't it? That's what it says. Now, what am I doing? Just see. It is showing that at the end, what it is showing, 5 rows, 785 columns. Why? Because I typed head of 5. Head of 5 means I will get 5 rows. Of course, how many columns? 785 columns. Why it is 785 columns? 28 by 28, 784 only. Why you are getting extra one column? Extra one column is label column, isn't it? That's why I removed label, dropped label. Now I'm printing print d.shape. Everyone knows what is shape command in Python. What it says, 42,000, 784. My dear friends, in the Wikipedia, what it says, there are 60,000 training images, but this particular data set I downloaded from Kaggle, but Kaggle is having only 42,000 images. It's not giving 60,000 images, but Kaggle, I think maybe you can check from other dataset websites. Of course, it doesn't matter whether it is 60,000, 10,000, 1 lakh. It doesn't matter. Concept is very important. Yes. Now, what is my dataset here? I request all of you to understand about dataset. What is my dataset here? 42,000 means 42 here. How many columns? 784 columns. What is the dimensionality of this data set? Dimensionality of this data set 784. What is my intention? I have to convert this into X dash whose size is 42,000 by 2. The 784 dimensions I will convert into 2 dimensions so that you can visualize data. Not only visualization, it has got its own applications. We will try to understand. Maybe if I explain first time, you may feel a little bit difficult. Just refer. I recorded each and everything with minute details. By tomorrow, just if possible, go through that videos. Certainly you can understand. Yes, actually I have 42,000 data set in which what am I doing? I am collecting only 15,000 images. Head 15,000 means top 15,000 images only I am collecting. You may ask me why you are taking only 15,000. Why not you are taking 42,000? Why? Because while executing code, it will take little bit more time. 42,000 images means your Python code will take few microseconds or few microseconds more than this one. That's why just I am restricting myself. With 15,000 images. From that 42,000 images, just I am collecting only 15,000. Top 15,000, head 15,000. Head 5 means you are getting 5 rows. Head 15,000 means I am getting. Now I would like to work with only 15,000 images. For that matter, you can work entire 60,000 images also. It doesn't matter whether it is 15,000, whether it is 42,000. It really doesn't matter, isn't it? Yes. Now what am I doing? Just see, my dear friends. This one. Just see the shape of the sample data. This is sample data. Originally, you have 42,000 images. Now I collected a sample. What is the shape? 15,000 by 784. Original is 42,000 by 784. Now I have a data set. Now I have got a data set whose size, let me say my data set size is 15,000 into 784, isn't it? Yes. For this, I have to reduce this 784 dimensions into 2 dimensions. For that, what I need eigenvalues and eigenvectors. Here difficulty is not square matrix. It is not square matrix. I will convert into square matrix. There is something like covariance matrix. I will try to calculate covariance matrix so that I will get why we are calculating covariance matrix. I request all of you, all participants, why to browse this one and remind me in tomorrow's session why we are using covariance matrix for finding eigenvalues and eigenvectors. Is there any other possibility? Can we find some other matrix for which you have to calculate, for which you can calculate eigenvalues and eigenvectors? If I forgot, please remind me tomorrow. Now what am I doing? Yes, see. From sklearn, scikit-learn, this is one of the important machine learning package, very important for pre-processing. There is something like standardization. There is something like column standardization. Column standardization. There is something like pre-processing. I request all of you. I recorded lecture on pre-pro. That is why do we need some sort of. I request participants to mute yourself. Someone is discussing something. Yes. There is something like in probability there is something like standard normal distribution whose mean equal to 0 and standard deviation equal to 1. There is simple mathematical concept behind it. As I have got some time constraints, I'm not going into that. But if someone is interested, certainly I recorded lecture. Just go through it. Yes. What am I doing? Standard scalar dot fit underscore transformation. Data means what? My sample data. This is my sample data. I'm standardizing this. What is a standardization? Why do we need standardization? Why it is important? Just go to standardization of data. Just I will show you. This is the this is in sklearn dot preprocessing dot standard scalar. There is a this is a particular function. I request all of you to study this particular method. Just see that's what just see the beauty. Just see there is something like all of you in your engineering classes might have seen this formula many times. Which formula? This formula. Just give me 1 minute time. There is a formula z equal to x minus mu by sigma. X is normal variable, z is standard normal, mu means sigma means standard deviation. Just see this. What is just he will just see the standard score of x. Somewhere he will write. Just see s is yes. S is the standard deviation. What is my s? Here mu is standard deviation. Here u is mean. You just see here u is the mean of the training sample. In the case of standardization, what you are doing, you are converting all sample points with the mean mu equal to 0 and standard deviation equal to 1. Means simply I can say you are converting into standard normal distribution. Why we have to convert into standard normal distribution? What is the intention behind it? Just I request all of you go through that standardization lecture. It may not permit me to discuss all those things. Yes, no. I did some sort of pre-processing. I standardized data. After standardization, I just remember, my dear friends, before standardization, my data set size, I think maybe can we take 5 minutes break, dear participants, so that I will take little bit water and tea.
Okay, sir.
Can I take 5 minutes break? I think it's
Okay.
12. Okay, thank you.
Okay, sir.
Only 5 minutes. I will take 5 minutes break. Let me have tea and water. Even you can also relax yourself. Just let me stop. Only after 5 minutes I will join. I will be here only.
All the participants, please take 5-minute break. After 5-minute break, again, we'll continue the session.
Sir, your voice is not coming.
Sir, just 5 minutes break, sir. I will join after 1 or 2 minutes. Yes, am I audible?
Yes, sir. Yes.
Okay.
Yes, sir. Yes, sir.
Yes, let me continue my discussion. I think the screen is also visible.
Yes, sir.
Am I right?
Yes, sir.
Yes, actually, what we did before standardizing data, your data set size is 15,000 by 784. Even before standardization is also size is 15,000 by 784 only. Standardization does not change data set size. That is important point. Only it will. That's what I tell. That will make use a formula known as z equal to x minus mu by sigma. That's what he is explaining in scikit-learn. You see, in the scikit-learn what they are saying. What is standardization means? They are doing some sort of transformation. They are applying simply they are applying this transformation. It is simple. For example, what they used to do, they used to take a column. Column standardization means, you know how to calculate these points, these numbers. You know how to calculate standard deviation. You know how to calculate mean. You know pixels. Just applying transformation. They already written code, that's a built-in thing. Just it doesn't alter the size of the matrix. Before applying and after applying standardization, your matrix size is same. That is 15,000 by 784. Yes. Now that standardized data, where am I keeping? In a variable known as, just see here, comment section, what? Covariance matrix. Why do we need covariance matrix? What is the reason? I need eigenvalues. I need eigenvalues and eigenvectors for dimensionality reduction, but my data matrix is of size X of 15,000 by 784. If I want to calculate eigenvalues, I need square matrix. But here I have rectangle matrix. In order to get a square matrix, I am calculating this. How to calculate covariance matrix in your primary classes, in your matrix and calculus classes, there is a formula A transpose into A. For a given matrix A, just calculate A transpose into A, you will get covariance matrix. That is the formula. Yes, my question is, for finding eigenvalues, vectors, is it the only way? Is there any other way? Yes, certainly. I request, that's why just browse for in the context of principal component analysis. Can we make use only covariance matrix? Is there any other matrix for which you can find eigenvalues and eigenvalues? Just it's a question. Just remind me next session, that is tomorrow's session. Yes, this is my sample underscore data. Yes, what is my sample underscore data? What we did here, standardized data is in this variable. That standardized data, that is standardization means I already explained. There's something like Z equal to X minus mu by sigma. In this context, they are saying X minus U by S. After standardizing, I'm keeping in a variable known as sample underscore data. Now I have to calculate covariance matrix, covar underscore matrix. NP, what is NP? Import NumPy as NP. All of you know what is NumPy, isn't it? In NumPy, there is a command, there is a method matmul. Matmul means what? What is the meaning of matmul? Matrix multiplication. Matrix multiplication. Which one? How? What is the formula? A transpose into A. How can I find covariance matrix? What is the formula? A transpose into A. What is my A? A sample underscore data. This sample underscore data matrix is A. This is A. Yes, this is A transpose. Isn't it? I'm multiplying A transpose A. Which one, my dear friends, what is my sample matrix here? My sample matrix, sample underscore data. What is the size of sample underscore data? What is the size of sample underscore data? Is anyone? Sample underscore data size. Sample underscore data size is, let me say sample underscore data, let me represent by X. This X size is, just try to recall, 15,000 by 784. I am representing sample underscore data with the matrix X 15,000 by 784. What am I doing here? Sample underscore data dot capital T. Dot capital T means what? Transpose. What is the transpose of this matrix? You will get 784 by 15,000. This is transpose. This is sample underscore data cap dot T. And sample underscore data, what is sample underscore data? Sample underscore data is 15,000. Just see, I'm multiplying sample underscore data dot capital T with sample underscore data. That is 15,000 into 784. If I multiply, what will you get? You will get a matrix of order 784 by 784. Are you getting square matrix? Yes. This is square matrix. My dear friends, what is my sample underscore data? My sample underscore data is 15,000 by 784. Sample underscore data dot t means 784 by 15,000 into sample underscore data means 15,000. You will by 784 matrix. That is covariance matrix. Now you are getting covariance matrix whose size is 784 by 784. Now I have got a square matrix for which I can always calculate eigenvalues, isn't it? Just see. From SciPy, those people who are really working in machine learning, there is a library, SciPy library, sklearn, SciPy, all these are very important libraries. LinALG. If please type and search in Google search. LinALG means linear algebra. What is this LinALG means? In introduction itself, we were saying linear algebra has got so much of role. If it's something is working for 2D to 1D, it will work for ND also. That's the power of linear algebra. You can extend this, isn't it? Yes, LINALG means linear algebra. You are importing EIGH. This is EIGH. This is a built-in command, built-in method or function in which, my dear friends, what is, let me express my covariance matrix as S. What is the size of S matrix? What is the size of my covariance matrix? S is 784 by 784. That is my S, isn't it? Now, for example, in your BTech classes for 3 by 3 matrix, if you have 3 by 3 matrix, how many eigenvalues you will get? You will get 3 eigenvalues, isn't it? You will get characteristic equation of order 3. In similar manner, for this particular matrix, yes. What is my S? My S is covariance matrix. EIGH is a command, method, function for whom I am giving covariance matrix. What is the covariance matrix size? 784 by 784. EIG, VALS, eigenvalues. What it says? 782, 783. What does it mean? This 784 by 784 matrix will get how many eigenvalues you will get? Lambda 0, lambda 1, lambda 2, lambda 3, so on, lambda 782, lambda 783. Why? Because 784 eigenvalues you will get, but as it starts with 0, I am ending with 783. Now, the beauty of this particular command is, what will it do? It will find all eigenvalues. 784 eigenvalues it will find. After finding eigenvalues, it will arrange like this. Lambda 1 less something. It will arrange some increasing order. Yes, EIGH 78, let me say like this. After finding all eigenvalues, what is the relation? Lambda 0 less than lambda 1 less than lambda 2 less than lambda 3, so on so forth. Lambda 782 less than lambda 783 means not only it finds eigenvalues, after finding it will arrange all eigenvalues in this particular order. It will identify, once if I say I am asking it to return 2 eigenvalues corresponding to lambda 782, lambda 783. What does it mean? Why you are asking only for 2 eigenvalues? My intention is to reduce to 2D. My intention is to reduce 2D. Isn't that's important? That's why I'm taking 2 eigenvalues. If I would like to convert into 3D, I would have told you 781, 782, 783. If it is 4-dimensional, like this, you can extend, isn't it? No. In all eigenvalues, the largest eigenvalue is 783. Next to largest is 782. That's important. Those eigenvalues will get stored in a variable known as values. Corresponding eigenvectors will get stored in vectors. Now, what we achieved? We find actually eigenvalues and eigenvectors plays major role. It is something like projecting things from higher dimension to lower dimensions. Here there is something like perpendicular distance from a point to plane. All those things you need little bit intuition. If someone is interested, just go through the lectures which I recorded. Yes, now I have got eigenvalues as well as eigenvectors. What is this values? What is this vector? These 2 vectors are the topmost eigenvectors among all 784 eigenvectors. No, I must say like this. Let me say like this. These two eigenvalues, which two eigenvalues? These two eigenvalues are the topmost eigenvalues among these 784 eigenvalues, and these two eigenvectors corresponding to topmost eigenvalue. This is the story. Now what we have to do? Just see. Shape of the eigenvectors, what it says. Just see, my dear friends, just see how many eigenvectors I found now. Shape of the eigenvectors, vectors dot shape. What it says? Shape of the eigenvector 784 by 2. 784 by 2 means what? What is 784 by 2? Yes, for actually we made little bit of transpositions. What I am doing now, converting eigenvectors into 2D shape. I am converting it 2D for easiness of processing. Vectors dot capital T means transpose. This 784 by 2 will become 2 by 784. That's what it says, 2 by 784. Actually 784, you need not be in hurry. Let me spend few minutes here. Just see here what's happening here. Let me explain this part. Shape of the eigenvectors. How many eigenvectors we found? 2 eigenvectors. What is its shape? 784 by 2. 784 by 2 means what? 1, 2, 3, 4, 5, so on. 784 by 2 means this is 1, this is 2. Let me say V1, that and otherwise lambda 1, lambda 2, isn't it? Lambda 1, this lambda 1 is 784 by 1 vector, or V1. Lambda 2 is another 784 by 1. I have 2 eigenvectors. Generally, for 3 by 3 matrix, what eigenvector you will get? Something like 1, 2, 3. You will get 3 by 1 eigenvector. For 784 by 784 matrix, I will get 2 eigenvector. First eigenvector is 784 by 1. How 3 by 1 eigenvector you will get for 3 by 3 matrix? In similar manner, I will get another eigenvector. This first column is first eigenvector. Second column is second eigenvector. That is 784 by 2. Isn't it? That's what the 784 by 2 says. Isn't it? Now what we are doing, just it is simple pre-processing step. In order to accommodate compatibility purpose, we are taking transpose. The 784 will become 2 into 784. Actually, we have to project this 784 dimensions into 2 dimensions, means it's basically dot product. It is basically matrix multiplication. Matrix multiplication means you are projecting thing to another dimensions, isn't it? Now what I am doing, updated vectors. Why am I request participants to mute yourself if there is anything to discuss? Certainly we will discuss. Yes, actually here what am I doing? Now I am bringing into new coordinate system. Wow, I would like to import matplotlib. .pyplot as PLT. Maybe matplotlib, maybe many of you might have seen this matplotlib data visualization package. There is another one, Seaborn in Python. What am I doing? Import NumPy as NP. NP is alias for NumPy. Matmul means matrix multiplication. What is the vectors? Vectors means what? Just now we were saying what is vector. Vectors means what? Updated one. Updated one means what? This you are multiplying. Which one you are multiplying? Your updated one is 2 by 784. We took transpose, isn't it? What is this sample underscore data dot t? This is 784 by 15k. I have to multiply. Just see, that's what it says. You are multiplying. You are multiplying with 2 eigenvectors with the original matrix. Your original matrix size is 15,000 by 784. Isn't it? Of course, in order to accommodate matrix multiplication, I'm taking transpose, isn't it? If I multiply these 2 matrices, what will you get? You will get 2 by 15,000. Means what if you take transpose, you will get 15,000 by 2. Actually, your original data set is 15,000 into 784. Now you are converting into 15,000 into 2, 784 with the topmost eigenvector. With the topmost eigenvectors. Earlier we were discussing that there are 2 features, feature 1, feature 2, age, heights, which has got less variance, age has got less variance, drop it and retain heights, like that. That we are manually doing, but mathematically that's the beauty of covariance matrix. But if you find eigenvalues and eigenvectors for covariance matrix, you can get topmost eigenvectors topmost through the top, even you can say now anyway, just see this new coordinates here. Principal components means just I'm displaying. You see what it says, pd dot data v stack means vertical stack, and pd dot data frame. Just I'm displaying first principal component, second principal component. Just see this is first principal component, second principal component. Labels means 0 to 9, any label corresponding principal components, isn't it? For simplicity, I am displaying only few values here. Just see data frame dot head. Head means only first 5 I will display, isn't it? Now what's happening here? Here just I'm displaying things. Just see, you might have seen this one. What it says, Seaborn as SN, import Matplotlib. Of course, Matplotlib works over Seaborn. Basic package is Matplotlib. What am I doing here? I'm adding legend. Of course, here in PPT it's not showing. I will show. I will share that IPython notebook. You can see it. I'm just see. I'm displaying with the scatter plot. What is this plot name? PLT dot import PLT dot scatter means scatter plot. First principal component, second principal component. Isn't it? Hue. Maybe most of you may know hue parameter. Hue parameter means depending on this label it will display. Hue code label means what are the labels in this particular data set? Labels are 0 to 9. Hue code label means depending on this labels it will display the data set, isn't it? Just see this one. Actually what it says, just see labels. What are the labels here? There are colors. Hue parameter means depending on the colors. Just see 0, 1, 2, 3, 4, 9. This color pixels, this color pixels is 0. This color pixels are 1. This color pixels are 2. This color pixels 4, 5, 6, 7, 8, 9. But if you see this, there is some problem with, isn't it? Just go to this that blog. Which blog? Christopher Ola. As I told you, I'm strictly following this particular blog. Just see. MNIST data sets. Same thing. He says same thing. Just play this one. Just see the colors. You can see the. Just see. If I select, it will show the numbers. Like this, it will show, isn't it? This is visualizing MNIST. Of course, there are different algorithms. This MDS, I'm not discussing about MDS, Siemens mapping. Just it will show the numbers also like this. Yes, this is Tisne. What is Tisne? I will discuss. Just compare. I request all of you just compare your visualizing MNIST with Tisne as well as PCA. After some stage, what happens in the case of actually in that PPT, I'm showing just one particular instance output, isn't it? In the case of MNIST with Tisne, of course, what is Tisne? I will explain. In the case of MNIST with Tisne, what happens after some stage that pixels are getting separated? Just see, these pixels are related to 7. They are coming into one position. These pixels related to 3. There is a clear separation. Just see, this is 5. This is 0. This is 5. Yes, this is 8. Just see. Sometimes what happens, just see, your 8 pixel is sometimes closer to 3 pixel. Why? Because 3 shape is little bit similar to, people may write your 3 is almost like 8. There may people who write 5 similar to 8. That's why it is showing like that. But my request is just observe output of visualizing MNIST with Tisne, and as well as just see, this is Tisne plot. Clean separation. All points are cleanly separated. Just see, a Tisne plot with MNIST. But in the case of PCA, but it is not the case with PCA. In the case of PCA, there will be just visualizing. Just see here, visualizing MNIST with PCA. Just see our output. There is so much of overlap. There is so much of overlap. There is so much of overlap in the case of, there is so much of overlap in the case of MNIST. But in the case of Disney, after some stage it will settle down. Just see a Disney plot. The clean separation. Yes, there is a clean separation of the points, isn't it? Yes, just of course there are other techniques, but usually the famous techniques are PCA as well as Disney. That's why here your output is, it's overlapping. Just see here, there is so much of overlapping is there. Yes, yes, my dear friends, I would like to highlight one point. There is something like cumulative variance. Actually, in initial discussion itself, what we were saying, variance. What is the use of eigenvalue? What is the use of eigenvalues? Eigenvalue represent variance, isn't it? Yes. There is something like cumulative is just a CUM, cumulative variance. What they used to do, they used to calculate cumulative variance is nothing but this one. Let me say I have lambda 1, lambda 2, lambda 3, 3 eigenvalues. Let it be. How can I calculate cumulative variance? Lambda 1 by lambda 1 plus lambda 2 plus lambda 3, lambda 2 by lambda 1 plus lambda 2 plus lambda 3, lambda 3 by lambda 1 plus lambda 2. For example, there are 783. How can I calculate cumulative variance? Lambda 1 by lambda 3 plus so on lambda 784. Here plus so on so forth 784. Here also so on so forth lambda 784. Last one is lambda 784 by lambda 1 plus lambda 2 plus so on lambda 784. This is cumulative variance. That's the basic concept. My dear friends, here I would like to highlight one point. Why? Because this point is very important. Yes. Anyway, this code also I explained in detailed manner in recorded video. Why we are recording videos means we may not get enough time to spend. We may not get enough time to spend. Therefore, if it is recorded anywhere, anybody can go through it. Anybody can understand. That's the basic intention. Let me show this graph. This is a graph. What we are doing here. Just see. Here, how many eigenvalues are there? There are 784 eigenvalues, isn't it? Now, my first intention, of course, I know it's a 12:46, it's the time, but let me take 2 minutes here. What I'm doing here, just understand. My first motivation is why do we need dimensionality reduction? Visualization. Why? Because higher dimension you cannot visualize. Second is applying machine learning algorithms. Why? Because on higher dimensional data, there are many machine learning algorithms which cannot be applied. For example, there may be a machine. I would like to apply MNIST. I would like to apply some machine learning algorithm. This MNIST data set. For example, that machine learning algorithm needs only 100 dimensions, which cannot work for 784 dimensions. There may be some machine learning algorithm which may work only on 250 dimensions, isn't it? That is another point. Here, one of the biggest question is, originally there are 784 dimensions. When we had 784 dimensions, I have 100% of data. I have entire data when I have 784 dimensions. My question is, let me say like this. I want to let me otherwise. I want to say something like this. Let me show in this graph. Let me say some 100. These are the principal components. Let me say if I would like to retain something like this one. Let me say originally, again I will repeat. There is nothing wrong in repeating good things many times. If I had 784 dimensions, I have 100% of data. Now, just see, this graph is also just see, till 784 only you have this graph, isn't it? Now, my question is, if I reduce this 784 dimensions into 100 dimensions, I would like to convert this 784 dimensions to 100 dimensions. How much data? Let me change color otherwise. how much data can I preserve? How much data? How much data can I retain? Can I retain? How much data can I preserve? That is question, isn't it? In that case, what I have to do? I have to plot this one, cumulative explained variance on y-axis, number of components on x-axis. How many components? There are 784 components. As this matrix size is 784, your square matrix size. I'm taking this components on x-axis, explained variance on y-axis. I already discussed what is explained variance. Now, I would like to know how much of data can I preserve if I reduce to 100 dimensions. In that case, what you have to do? Just go to 100. Just go. Identify corresponding point on this plot. Just go here. What is this value? What is this value? It is in between 0.6 and 0.8. Let me assume this is 0.75. Let me assume let it be 0.75.